Welcome back, everybody. So again, just check out your section 8.1 homework and check your answers. Everybody following along at home. I've already gone through this by in class, so just pause and check the homework where you need to.
How many people do we even have at home?
But that's just like if anybody's out, like anybody's sick, like York can watch this. And do
we have any online students left?
Oh yeah. Oh yeah. Okay, so there was a question about number 8. Wrong PDF. There we go. The total cost of electricity for a particular light bulb varies jointly as the time t that the light bulb is used and the cost k per kilowatt hour. And C is 12 when t is 50 and k is 6. All right, so I'm going to use that first sentence to kind of set up what I need to set up there. The cost of electricity varies jointly as the time t. So again, this is the one where I'm going to just find a new variable for my constant variation. I'll use the same that they did. M varies jointly as the time t and the cost k per kilowatt hour. Okay, so there's our formula. And then it says C is 12 when t is 50 and k is 6. So I just have to solve this equation. So that's going to get me 12 divided by 300, really. Okay, so we got 50 times 6. That's where I got that 300. And then I'm going to take 12 divided by 300, and that's going to give me 0.04. 0.04 is my m, my constant of variation. So I can create my new equation. C is equal to 0.04 tk. And now it says find c to the nearest cent when t is 30. So c is equal to 0.04 times 30 times my kilowatt hours is 8 cents per kilowatt hour. So 0.04 times 30 times 8 gets us 9.6 to the nearest cent. So $9.60. Yeah. Or no. That's just cents. So it's just 10 cents. 10 cents, right? C is equal to 9.6. So to the nearest cent, we need 10 cents. Let me just double check on that. Yeah, 9.6, so 10 cents. Any other questions on the homework that we want to talk through? No? Okay, let's get to our notes then for today. Moving right along. So yesterday I kind of introduced the idea of what a rational function was, right? Where I had said, we had never really studied when we put an x in the denominator of a function, right? And that's really what we're going to be looking at pretty much the rest of this chapter. What happens when we put an x into the denominator? Now, obviously, we've got to operate with these rational expressions. So we're going to learn how to add, subtract, multiply, and divide with them. All right, so I guess we should first start off with what is a rational function? What is a rational function? Well, in lesson 8.1, we worked with an inverse variation such as 5 over x. The expression on the right side of this equation is called a rational expression. Any rational expression is one that can be written in the form of a fraction. Okay, the quotient of two polynomials. Now remember that polynomials could reference monomials. They could be talking about monomials as well. So that's why just a 5 over x is really a quotient of two polynomials. As long as there's x into the denominator, you'll get a rational expression. These are some types of rational expressions. You don't have this in the guided notes, just kind of like a little intro there. Because rational expressions are ratios of polynomials, you can simplify them the same way we simplified fractions. Remember back when we first started doing those that fraction review day one, and I said, okay, I want to talk about how we think about simplifying fractions. And I want to shift the way we think about simplifying fractions. I want to say, instead of thinking about what can we divide out of both the numerator and denominator, I want us to think about what common factor can we cancel out of the numerator and denominator. Like for something like this, we looked at this example where we looked at 9/24, and we saw that there's a common factor of 3. Once I got it reduced down to its prime factorization, I saw a common factor of 3 that was common in both the numerator and denominator and could cancel out. And that's why we think about dividing out a 3, canceling out a common factor of a 3. When identifying values for which a rational expression is undefined, identify the values of the variable that make the original denominator equal to 0. You're going to see me say, identify, you can see it up on the top of the page there, identify any x values for which the expression is undefined. What I mean by that is, when is a fraction undefined? When a 0 is in the denominator. So you're looking toward finding things that will make the denominator 0. That's what will make this this expression undefined. You're looking for what would make the denominator equal to 0. Now, I'm looking at my page and your page, and I think I don't have example A up on my page, so I need to kind of shift that around. Or maybe where is it? Is it anywhere here? No. Okay, I got it. All right. So here's what we're gonna do. We're gonna go like this, and we're gonna put it. Okay. And we're gonna say this is 10. X to the 8 over 6x to the 4. All right, and that is gonna be B. Okay. All right, so let's take a look at example A here. Okay, example A. Now, notice that this is a quotient of 2 polynomials, right? This is a quotient of 2 monomials. So I'm going to reduce this fraction. Now, we know how to reduce this fraction. We've worked with this fraction before. We've seen these things before. So what are we going to do? Well, I got to think about what common factors are there in both numerator and denominator. You know, I know that I could just subtract. The rule is we subtract the exponents of the variables, right? That's the rule for dividing those things. But what made that rule happen? That rule existed because, well, let's prime factor down both numerator and denominator. This was like a 2 times 5 times 1, 2, 3, 4, 5, 6, 7, 8, right? Well, that's the prime factorization of that. Okay, well, this is 2 times 3 times 1, 2, 3, 4. So I wanted us to shift our thinking into figuring out what can cancel in both numerator and denominator, because now I see, look, and then 1, 2, 3, 4 sets. Whoop, I got carried away there. There we go. The 2's cancel, and then we got 1, 2, 3, 4 sets of x's canceling, right? So we know that this will reduce down into 5x to the 4th over 3, right? Now, I know in your brains you're doing something different. You're saying, okay, 10/6 reduces down into 5/3 because both of them will by 2. X to the 8th over x to the 4th, 8 minus 4 is 4, and that's where I get the x to the 4th in the numerator. Yeah, that's great. But what I want to show you is, why is that happening? That's happening because you can cancel out a common factor of 2 and cancel out 4 common factors of x's. And then you'll leave an x to the 4th in the numerator. Okay, so let's take a look here. Let me do this. Let me bring this guy over here. There we go. A little smartboard magic. This is your example. This is your example C, correct?
Yeah.
Is that correct? Okay. So let me go here and we'll do example B. All right. Now, Whenever I ask you, oh, I forgot to do something up top. What would make this expression undefined? Is there any x value that would make the expression undefined? Zero. You have to go back and look at the original expression. Okay? You have to go back and look at the original expression and say, okay, what made the original expression undefined? If I plug in x, if I plug in any x value to the original expression, would anything make it zero? Yes. When I plug in 0, it would be undefined. So here's how we write it. X cannot be 0. When I ask you to identify any x values for which the expression is undefined, you're going to say x not equal to, and then whatever values of the variables that would make the denominator equal to 0. Okay, let's take a look at example B here. X squared plus x minus 2, x squared plus 2x minus 3. So what did we do? Every time we were reducing fractions, I said, get it down to its prime factorization and cancel out common factors. So now that it's a polynomial, I'm going to do the exact same process. I'm going to get it down to its fully factored form and see if there's any common factors I can cancel. Okay? Because can I think about it like I do numbers where I say, oh, I'm just going to divide something out of the top and out of the bottom? I can't do that. I can't think about it like that because these are polynomials. I can't just easily see what's divisible in numerator and denominator. So what we have to do is factor both numerator and denominator and see what happens. Let's quickly factor both numerator and denominator here. All right, factors of -2 that add to get to +1. X plus 2x minus 1. I'll just tell you right now, the better you are at factoring, the better you will be at chapter 8. Factors of -3 that will add to get to +2. X plus 3, x minus 1. +3, -1. What do you notice both numerator to denominator? The x minus 1's cancel. The x minus 1's cancel.
And the x's cancel too?
No, the x's do not cancel. And that's something that I really wanted to point out. Thank you for bringing that up. I've got an x plus 2 over x plus 3. The only things that will ever cancel are products. Products, okay? Like, for example, if I look at this number, I say 2 plus 3 divided by 2 plus 7. Can the 2's reduce out? Will this fraction become 3/7? No. It's really 5/9, right? That fraction you can't reduce it like that. You can reduce out products of things. That's why we get it down to its factorization. You can reduce out things that are products, but you cannot reduce out things that are just summed together, added together, okay? So no, in short, no, those x's will not cancel. The only things that will cancel are things that are multiplied. So here's my answer. And what can x not be? What x values is this expression undefined? -3. I like that answer. And there's something else. It's not 0. It's not 2. It's not -2. +1. Guys, I don't care what's happening in the numerator. The numerator can be whatever it wants. The numerator can be 0. I don't care. Can you have 0 divided by a number? Sure, that's just 0. But the denominator cannot be 0. Right? The denominator cannot be 0. What two values would have made the original denominator equal to 0? +1 and -3. +1 and -3. That would have made the original denominator 0. So that's part of my answer. Okay. Let's keep it going. 6x squared plus 7x plus 2, 6x squared minus 5x minus 4. This is your example C, right? That's good. All right, so again, like I said, the better you are at factoring, the better you'll be at this stuff. So let's factor around. I like to keep myself organized. I'm going to say I'm going to factor down the top, and then factor down the bottom, and then we'll see what happens when I start to cancel. Especially when these are two hard type problems. Now, can I cancel the 6? No. I cannot cancel the 6. Even though it is being multiplied, that term is still being added to another term. You cannot just cancel out the 6s. You have to get it down to its prime factorization before you start canceling out. So let's get the top down to the prime factorization. 6x squared plus 7x plus 2. All right, 6 times 2 is 12. Factors of 12, this is the master product method. Remember this a long time ago? 6 times 2 is 12. Factors of 12 that add to get to 7 are 3 and 4. And we break up 7 to be 3 and 4. 6x squared plus 3x plus 4x plus 2. And then we factor by grouping. We just took our chapter test on this on Algebra 1. 2x plus 1, 2x plus 1. So we get a 2x plus 1, 3x plus 2. I do the same thing for the denominator. I have a 6x squared minus 5x minus 4. So negative 24, factors of negative 24 that add to get to negative 5, are negative 8 and positive 3. Negative 8, positive 3. So that gives us a 6x squared minus 8x plus 3x minus 4. We factor by grouping here. Pull out a 2x, leaving a 3x minus 4. Pull out a 1, leaving a 3x minus 4. So fully factored form here is 3x minus 4, 2x plus 1. Okay, so top and bottom are fully factored. Like, what are we doing equivalent to what we do with numbers? That was just doing like the factor tree, right? Getting it down to its prime factorization so that we can see if any factors will cancel. Let's take a look at both numerator and denominator. So I've got 2x plus 1, 3x plus 2, over 3x minus 4, 2x plus 1. What will cancel? The 2x plus 1. Leaving me with a 3x plus 2 over 3x minus 4. Now, will the 3x's cancel? No, that's being added with a 2 and a minus 4. Those will not cancel. Okay, I take a look. Can I factor the numerator and denominator anymore? Nope. So there's nothing else that will cancel out. All right, so now that's my answer. And now I have to say what x is not equal to. Now, remember, where do you look to see what x cannot equal? The denominator, the bottom. So look at the right side. What would make, and when I say the right side, I'm talking about the factorization of the bottom. What would make the denominator equal to 0?
1 and 1/3.
Not 1 and 1/3, no. What would make the denominator equal to 0? Okay, basically, I'm asking this. Solve that. Right? I want to solve that. That is what's going to make the denominator equal to 0. So 3x minus 4 cannot equal 0, and 2x plus 1 cannot equal 0. Well, the solutions of that, add the 4, divide by 3. X is equal to 4/3, or not equal to, excuse me. And x is not equal to negative 1/2.
Hey, I said 1 and 1/3.
Oh, I didn't realize you were saying a mixed number. We don't do mixed numbers here. I thought you were saying 1, 1/3. So you meant 4/3. I gotcha. Then you were right by saying 1 and 1/3. I would have said 4/3. He was like, wait a second. Wait just a minute. So x is not equal to 4/3 or negative 1/2. I don't think he's ever been.
He was so offended.
All right, let's keep it rolling. Any questions on that one before we move on? Okay. This is your example E, correct? Oh, D, I'm sorry. Oh, that was right there. We're good. All right, so the process is factor it down, identify any common factors. So let's do it. Let's factor down the numerator. Fortunately for us, the numerator is a very easily factorable thing. We take out an x. We're left with a 4 minus x. Actually, you know what I'm going to do first? I don't like that. Never mind. What's wrong? What's weird about my top? It's not standard form. Let's put it into standard form. What I mean by that is I'm going to take this and turn it into negative x squared plus 4x. Negative x squared plus 4x. And now my GCF is not just going to be an x. It's going to be a negative x. Because I lead with a negative, you pull out a negative. So negative x leaving me with an x minus 4. And the denominator is very easily factorable because it's an easy type. Factors of negative 8 that get to negative 2. Let's go straight over here. X minus 4, x plus 2. So what cancels? The x minus 4s. Leaving me with a negative x over x plus 2. So what can x not equal? Negative 2, positive 4. You look at the denominator and you say, okay, a positive 4 would have made this equal to 0. A negative 2 would have made this equal to 0. So positive 4, negative 2. Take a look at our last one. Last one to the front. 10 minus 2x over x minus 5. Now let's take a look here. I'm going to put it into standard form again, negative 2x plus 10. And I see it leads with a negative, so I'm going to pull out the negative. GCF is negative 2, leaving an x minus 5 over an x minus 5. Okay, that's fully factored down. So what I can do now, cancel, leaving me with just a negative 2. See, this is a weird one because there's no more x's in the denominator. There's no more x's at all. So do I still have to identify where any x values would be undefined? Yes. Yes, even though there is no even x's in the final answer, you still have to say, well, x still cannot be equal to 5. Why? Well, because you always look back at the original problem. The original problem and say, what could x not be if I try to go back and plug things in? Yeah.
So when you're trying to find x cannot equal, should you always just do the original?
Always go back to the original denominator. Always. Always go back to the original denominator. And you look at the factored down version of the original denominator before you cancel things out. Numerator? No. The numerator will come into play when we start to graph it, but for where x is undefined, that's the denominator. Because the numerator can be 0. The denominator can't.
Why can x not equal the x not equal to 2? Because the negative 2 on the top on the numerator.
I don't care what happens to the numerator. Only the denominator. Yeah. The numerator can be whatever it wants to be. The denominator is restricted. It just can't be 0.
Okay.
Now, this section is titled Multiplication and Dividing of Rational Equations or Expressions. Have we done any multiplication and dividing yet? Not yet. All right, so flip it over.
Oh, that was, I thought that was it.
That was just reducing.
Oh.
That was just like reducing a fraction.
Oh, that's what my brain casted. I thought this was like, I thought we were done.
Where's it? The big pumpkin. All right, now, multiplying rational expressions.
What?
I thought somebody was playing this. Factor all numerators and denominators completely. Second step, divide out any common factors of numerators and denominators. Remember the whole cross-simplifying thing. That is going to be vital when we do this. If you don't cross-simplify, it will make your life so hard in the end. Because you're going to get a giant expression that you're going to try to factor down, and it's not going to work. Okay? You need to cross-simplify before you start multiplying. So we factor down everything. We cross simplify. Then once you're done simplifying, that's when we multiply through. Remember, think about fractions that we worked with numerically. We cross simplified, and in the end, we just multiplied straight across on top and bottom. And then you check to make sure that there are no more common factors. Okay? So let's try one here. Now, when I multiply and divide, we're going to assume that all expressions are defined. I'm not going to make you identify any undefined expressions when we multiply and divide. It gets too convoluted. All right, so we got 3x to the fifth, y to the fifth, because you not only would need to check this, you would need to check this, but when you're dividing, you need to check, because it'll keep change flip, you need to check both numerator and denominator, because they both exist in the denominator, so we don't even worry about it. So let's take a look here. I've got 4 monomials, top and bottom. I'm going to cross simplify right off the bat. Okay, I'm going to cross simplify. So go with your numbers here. 3 and 9. 1/3, right? 2 and 10. 5/1. Now, take a look here. I could choose to cross simplify, or I could choose to simplify top to bottom, and that's what I'm going to do here. X to the fifth over x to the third is x squared. Y to the third over y to the seventh, that's going to reduce down into a y to the fourth in the bottom. X to the third over x to the second is going to reduce to x to the first in the top. Y to the fourth over y to the fifth is going to be a y to the first on the bottom. So now I've reduced out everything that I possibly can. I look to my numerator, and I see a 1x squared times a 5x to the first, meaning a 5x to the third in the end. And I see a 1y to the fourth times 3y to the first, 3y to the fifth. And because I simplified before I started, I don't need to do any simplification. Yes?
Why did you simplify the 3x to 6 and the 9x to 6? Like the cross.
The cross simplifying because everything was multiplied. There's no addition or subtraction going on, so I can reduce this as the numbers. And then I could have reduced these if I wanted to. But I just think it's easier to reduce top to bottom than it is to cross. Okay, let's try again. Let's keep going with this. Now, this is no longer monomials, now I've got binomials. So the process remains the same. Reduce it down. See, the first problem, I didn't even need to reduce down anything, right? There was nothing to factor down. They were all monomials. Here, I've got things to factor. So, factor the numerator on the left. Done. Factor the denominator on the left. Pull out the 4. Factor the numerator on the right. Done. Factor the denominator on the right. That's the difference of squares. And now we cross simplify. My x minus 3's will cancel. My x plus 5's will cancel. Leaving me with, well, there's nothing remaining on top, so it's a 1, 4, and an x plus 3. You don't need to multiply things back together in the end. No, that's fine. You're just doing more work than you need to. Especially when it turns out like there's 2 or 3 binomials on the bottom. You can choose it. Sure, go for it. Boil it all out, but you don't need to. Yeah, you could leave it unmultiplied. Unmultiplied? The factored version of it. We'll say that. All right, take a look and see here. 10x minus 40 times, or divided by x squared minus 6x plus 8 times x plus 3 over 5x plus 15. All right, so the process is factor everything down and then see what will cross simplify. I mean, remember, the process is the same for what we were doing numbers. You know, when I was multiplying two fraction numbers together, I cross simplified using all the prime factors, and then I multiplied in the end. Same process. We're not changing the process. Pull out a 10 on the top left, leaving an x minus 4. The bottom factors, okay, 8, factors of 8 that add to get to negative 6 are negative 4 and negative 2. Top right factors into, well, it's just an x plus 3. That was a sneeze, I think. Pull out the 5, leaving an x plus 3 in the denominator on the right. Okay, let's cancel. Okay, we've got x minus 4s. We've got x plus 3s. And then look, the 5 and the 10 make 2 over 1. You said go brown. So that gives me just a 2 in the numerator and just an x minus 2 in the denominator. If you stay organized, it will help you. Yeah. Okay. Now, would we all agree that multiplication is very similar to division? Division is similar to multiplication when you're working with a fraction. Keep, change, flip, and you end up multiplying, right? So the same thing is going to happen with these polynomials. Oh, went to the wrong side. You can also divide rational expressions. Recall, keep, change, flip. What does that mean? Keep the first term, change the operation, flip the second fraction. Yep. Keep, change, flip. And then you multiply in the end. So let's take a look at this one. I've got 5x to the 4th over 8x squared y squared divided by 15, 8y to the 5th. All right, let's keep, change, flip. Keep. Try not to simplify before you keep, change, flip. Change, flip. Okay, try not to simplify before we do that step. Now let's simplify. Now let's figure out what can cancel. Because now I can see, oh good, 8s are going to cancel. 5 and the 15 is going to become a 1 over 3. And I see my x's here. I see my x's here will turn into an x squared in the numerator. I also see that the y's will cross cancel here and here, becoming a y to the 3rd in the numerator. You all see that?
Yeah.
And now we multiply straight across on top. On the top, I've got 1 x squared y to the 3rd. And on the bottom, I've got 3. There's my answer. Good. It's kind of like you feel really smart when you get to cross things out. It's like you feel smart about yourself. Like it's like a puzzle where things start like unlock, you know? I'm a nerd, I know. Self-described. Where'd that problem go? Oh, there it is. Okay, let's take a look here. X to the 4th minus 9x squared over x squared minus 4x plus 3 divided by x to the 4th plus 2x to the 3rd minus 8x squared divided by x squared minus 16. See, you can see where I could get pretty evil with this stuff. Like I could make some really messy factoring stuff going on, right? Like this, in my opinion, I mean, it factors pretty easily. We factor down the top. Well, let's factor down the left side. Oh, you know what? I'm sorry. Don't factor anything down until you keep, change, flip. You might screw yourselves up a little bit. Keep, change, flip. And now let's start to factor down. Numerator becomes x squared, and then an x squared minus 9. The denominator becomes an x minus 3, x minus 1. The numerator becomes an x minus 4, x plus 4. And the denominator becomes x squared. And then we'll have an x squared plus 2x minus 8. I can keep factoring. See, the numerator on the top left will factor into another difference of squares, x minus 3, x plus 3. And then in the denominator, I'm going to have an x minus 3, x minus 1. In the numerator on the top right, x minus 4, x plus 4. And the denominator on the bottom right will factor into an x plus 4, x minus 2. Can you see how the better you are at factoring, the easier this will be? So let's cancel. X minus 3's cancel. The x minus 4's cancel. Oops, that's a plus. Oops. Sorry. The x plus 4's will cancel. The x squareds will cancel, leaving us with an x plus 3, x minus 4, all over an x minus 1, x minus 2. See, here's where I'm saying you don't have to multiply it out. I'm okay if you leave it as its factored form within the final answer. There's one other problem that for some reason is not on your guided notes. I don't know, maybe there was a second page that got cut off somewhere.
A second page.
So maybe add yourself in another little, maybe come up here, because this isn't going to take you very much room. Okay. But you can solve equations using rational expressions too. And I want to show you a type of equation that's going to come out pretty nicely. This is especially when you have just a rational expression is equal to a number. This is a special case when it's a rational expression is equal to a number. I can think about this in two ways. I could straight off the bat multiply the x minus 5 over to the other side. However, I can simplify the left side to be an x minus 5, x plus 5 over x minus 5. And then do you see what happens? The x minus 5s will cancel, leaving us with an x plus 5 is equal to 14. So that means x is just equal to 9. Now, it says to check your answer. And the reason being is there could be a scenario where your answer may not exist. Let me say this. If this same problem, let me do this. Clone. Yeah, I say it like a robot. Clone. If this same problem had not been equal to 14, but 10. If this problem had been equal to 10, it would have factored the exact same way. It would have factored into x minus 5, x plus 5. The x minus 5 would still have canceled, but now in the end I would have had an x plus 5 is equal to 10, so x is equal to 5. What's wrong about that? X equals 5 is undefined. Look at the original problem. Where was the original expression undefined? 5. So 5 is not within the domain of that rational expression. Like if I had gone to plug 5 back in, you would have gotten 25 minus 25, or 0 over 0, which is undefined. you cannot have the denominator equaling 0. You cannot have the denominator equaling 0. This will never actually equal 10. Won't ever actually equal 10. All right, we'll stop there.